Welcome, Daan. I'm so excited to hear what you have to say today.
Oh, thank you. Yeah, like I said, I'm Daan. Happy to speak about a topic that's dear to my heart. And if Rebecca could show the term presentation, I can share my knowledge with you about this fascinating topic. So if you could unfold the introduction, because about 3 years ago, well, it's not the presentation, but the first um, in the doc representation, there's also folds. Just go slide down. And there's an introduction besides the Busy Beaver problem. Yeah. So about 3 years ago, I got into the Busy Beaver problem. I was familiar with the problem, but really didn't calculate things with it. And to me, it seemed like a very tangible problem that involved Turing machines. So without further ado, I'm gonna explain what the Busy Beaver problem is in a while. But we have to first introduce Alan Turing. So that's the next folded item. Alan Turing is maybe a well-known person that invented an abstract thinking machine that is basically the basis for modern-day computing, and it's his machine, although he created it to answer a mathematical question that is the topic of today. And let's look at an example of a Turing machine. So the next fold. So basically, what a Turing machine is, if you're not familiar, it's an abstract machine that has a tape, some state, and a program. And Rebecca, if you could click on the tape and go to the definition and show the full documentation of that. Basically, what a tape is a double infinite sequence of cells which contain symbols. And for the Turing machines that we're looking at today, these symbols are only a blank symbol or a non-blank symbol, and those are represented by either a 0 and a 1. And you can create a tape, an empty tape, by calling the tape.empty term. And the interesting thing with a tape is that it has a head that can read the cell and write to the cells that that's in. So, for example, the first code that we see on the screen, it will create an empty tape, and then it will write a non-blank symbol, and then we take a representation, and the text Q is just a symbol representing the head, and the convention is that the head will read the symbol to the right of that. And one of the other things that a tape can do is you can move the head on the tape, or you can move the tape respective to the head, and it can be moved in either direction, left or right. And if you execute that code that's on the screen, you will notice that the head has moved, and the reason that you only see a finite portion of the tape is that representing infinite amounts of sequence is hard. But if you look at the definition, so Rebecca, if you could um, scroll a little bit up and unfold the entire definition, you will see actually that a tape is a non-empty list of a pair of symbols and occurrences. And the occurrences, if you go to the definition, it can be either infinite or it can be finite. And that way you can represent the tape in its entirety without running out of memory. Okay, so that's the tape. The other thing that a Turing machine is made up is of state. So if you scroll down to where the slides are, at least if you call it slides, it's the presentation. Yeah, here we go. The state, if you will follow the definition, is nothing more than a wrapper around a natural number. So we can differentiate them, but they don't hold any more information. And the other interesting thing is the program. So if you scroll back to presentation and follow the program definition, yeah, this is okay. So program. So could you click the term program that's one up above the examples? Yeah, almost. That's the state. Yes, awesome. So a program is basically a set of instructions for a machine, and what a machine has is the tape and a state, and that forms a key into basically a map that allows an instruction to be run. So if you follow the instruction term in the definition, an instruction is either halt, which will halt the execution of the Turing machine, or do something. And what has been done is you write a symbol to the tape, you move the tape in a certain direction, and you transition to a new state. And that's what an instruction is. With instructions and a key, which is a pair of a state, which is the current state the machine is in, and a symbol that is read from the tape, you can look up in the program what the instruction is. So if you scroll down a little bit, you can see a representation of a program. You can visualize it as a table with which is indexed by the symbol, which is the symbol on the tape, and the current state. And on the cross section, there is either an instruction, or because the underlying data structure is a map, nothing is known. It's in the upper right table. There's a question mark, and there's not known what to be done for this instruction. So with all these things put together, you can create a machine, and we can look at an example. And if you scroll down to the presentation, and I think it's already folded open. Yeah, this is it. You have the program represented above, and the instructions aren't literal terms now, but they are strings representing a term. And how you have to read those is that the first character is either a 0 or a 1, and that's the symbol to write on the tape. The next character is either an L or an R, and that designates the direction to move in, and the next number basically is the state to transition to. So we have a program represented as a table, but you can also write that then as a unison term. And if you can then create a machine with that program and start it off with a tape that has 3 non-blank characters, ones, with a blank, and then 2 non-blank zeros, and you ask to run it for at most 100 steps, you will get the following output, and it is a trace of what the Turing machine will do. And you have to interpret this. Earlier we saw that the tape was represented by a letter Q, but here I chose to have some brackets or braces, and within the braces is the current state. So the first string is the Turing machine is in state 0, and again the right part of the tape is being read. And here you can see what the machine will do. So as an exercise, we know that in the first line the machine is in state 0. It's reading a 1 because it's next to the bracket. And if you look in the table, you will notice that on the cross-section of those combinations, it will write a 0, it will move right, and transition to state 1. And this is exactly what happens because zeros are subsumed by the infinite zeros that are on the left. It will disappear, and if you go through the manual steps, you will see that this is a correct execution of the machine. Does anybody know what this machine does in a more abstract sense? So what does this machine do for us? It's a hard question. Probably somebody in the chat will have answered that. So if it is given a unary representation of a number, starting with 0, so if you have 1, 1, it signals that it's 0, and every subsequent 1 is an increment. So with 4 ones, we have, or actually 3 ones, we have a 2, and we have a 1. And if we add 2 plus 1, we get 3. So we expect eventually 4 ones, and that's the last line as well. So this is basically a machine that can add 2 numbers by tallying it, basically. So, what has this to do with busy beavers? Well, the interesting thing about Turing machines is that Alan could prove that this machine, and that's the next fold. So if you scroll a little bit down, what Alan Turing noticed that this machine, although simple, is very capable. So it maybe doesn't come as a surprise anymore, but at the time that he thought up these things, it was a very novel idea, is that you could represent a Turing machine with symbols. Basically, you code a Turing machine, and in a sense, this model that I've just shown you is a testament that Unison is a powerful language because it can simulate a Turing machine. And Turing machines are maybe a standard of a computational device. And the fact that a Turing machine is capable enough to simulate itself is a mind-blowing thing. So that's a very cool thing. But I think it was Uncle Ben that said, with great power comes the halting problem. So the halting problem is the question, is there a Turing machine? And you can open up the definition. Is there a machine, a Turing machine H, that when given a description, so a representation of the function of a different Turing machine, and a representation of the input that you want the Turing machine written on the tape, that you want to execute the Turing machine on, is there a machine that can say, this Turing machine will halt? And halting is either stopping, and the opposite of halting is looping forever. And this will be a nice feature to have, that if you, without running the program itself, but was just inspecting the program to tell if a Turing machine will halt, if a program basically will stop. Unfortunately, that's not the case. There isn't a Turing machine H that can do this. And there's a sweet little proof that I will go over now. So if you unfold the proof and then unfold the assumption. So what we're going to do is we're going to assume that this machine exists, that this Turing machine H exists. And then we're going to create a new machine, which is the opposite. And if you unfold the opposite option. So if you have a Turing machine that can do what the halting problem basically asks, then you can also create the next machine, that is H prime. If you give it a description of a Turing machine, and you will use that to ask the original halting Turing machine if the actual machine that you're working on its own description, will halt. And if it does that, you will loop, and vice versa. So if you think hard about this, it's a bit mind-bending, but the following thing is that if you ask to evaluate the following sentence, if you have that machine that is capable of, if you have the halting problem, what would this evaluate to? So if you expand the impossibility, so if you unfold the impossibility, if you ask what the Turing machine H prime does with its own description, it should loop if H tells that the execution of H prime on its own description halts, which is weird, and vice versa as well. So if it should halt if it doesn't halt. So that's an impossibility, and because that's an impossibility, we have to check our assumption, and one of the assumptions was that there was a Turing machine that can answer the halting problem. So we have to come to the conclusion there cannot be a machine that does such a thing. Okay, so this is very sweet mathematics, at least to me, but it's also very hard. So what I want to make clear, and that's the particular cases that I want to discuss, is what's not being said. So what's not being said is that you can determine from a program if it will loop or halt. Because the above program, which immediately will halt whatever the tape is, or at least if it's run on the empty tape, you will know for certain that it will halt, because that's the first instruction that's going to be executed. And even a more complex program, which is the second program on the screen, you can determine by that this program, when run on the empty tape, will eventually halt. It will halt in 2 steps. So what's being said is there can be a Turing machine that will always correctly identify if a certain description of a Turing machine and its input will halt or not. That's amazing. What does that have to do with the Busy Beaver problem? So the Busy Beaver problem basically, and you can unfold the definition, is if you have a Turing machine with a number of states, and you start it on the empty tape, you call it a busy beaver if it is a champion. And there can be a number of champions. You can either write the most once on the tape with the n number of steps, but you have to finish eventually. You have to halt, or you have to take the most number of steps. And the interesting thing is that this is an uncomputable function. I haven't said what it is, but we already seen an example of an uncomputable function. A busy beaver function that there can be a Turing machine that calculates the busy beaver function. And how can you solve the halting problem with if you know the busy beaver number? So if somebody would give me a Turing machine, I can simulate it for a number of steps that is at least as great as the busy beaver number for that number of states that the Turing machine uses. And if it's not halted already, then it will run forever, because by definition, the champion of, for example, 37 states has the longest running time. And if there's a machine still running, it will never stop. Otherwise, it will be a champion. So this is a very powerful mechanism. If you know the busy beaver number for a number of states, then you basically can determine for that number of states if a Turing machine will halt or not without simulating it in advance. So this is the problem, determining the values, specific values for the busy beaver problem. And there are some known values. For example, if you unfold the known values tab, if you think about it long and hard, if you only have one state and you're starting on the empty tape, the only thing that you could do is basically halt, because if you do something else, it won't actually work. You will transition either left or right, and you encounter the same symbol that you just read, and that means that you will do the same thing. So if you started out moving right, you will keep moving right. You will never halt. So with a single state, the only basically says that in one state you can only do one thing. The other states I want to go through a proof, but when I started looking at this problem, line 5 had a question mark in it. So there was a suggestion what the maximum running time of a 5-state Turing machine was, but it wasn't proven. And I thought to myself, well, it seems a little bit big, but it's not that big of a number. And if you do some back of the envelope calculations on how many Turing machines there aren't that many Turing machines. So I did the math, and if you unfold the number of Turing machines, if you imagine that a program basically is maybe a bingo card with a number of cells that you have to fill in, that it comes to, for each cell that you have to give an instruction, and you either have to do something or you halt. And if you do something, you have two options for what symbol to write. You have two options for the direction to go in, and there is a number of states that you can transition to. So let's say if there are n states, and the total number of options per cell in your program is exactly 2 times 2 times the number of states plus the halting states. And because the cells are represented by either a symbol and a state, you have to multiply 2 times the number of state cells. In short, if you look at the number of Turing machines for a 5-state Turing machines, it seems a little bit big, but it's not astronomical big. There's a famous number called Eddington number, and it basically says that the number of protons in the universe is something along the lines of 10 to the power of 80. And it's nowhere near that number, because it has far less digits than 80 digits. So I thought to myself, how hard can it be? And apparently it can be very hard, because if you have to basically simulate every Turing machine, you will have a lot of work to do, especially if you have to run for that big number that was the known value of the prognosed value of the champion. So what I did was, it felt like this would be a tractable problem. This is big, but it's not enormous. So I wanted to have some feeling of could I crack this problem? And what I learned and thought about was that you can do some optimization, and that is of the following form. So first of all, you can do less, and if you do less work, you can do more work in the same time. And if you think about it, for a Turing machine with more states, the first thing that you have to think about is you have to think about what will I do if I'm in state 0 and I read a blank symbol, and you can just assume that it will not hurt you to write a 1 and either go left or right. If you have a choice, just go right, because that's the same thing as doing left only looking at it in a mirror, and go to a next state, because we already saw that if you go to the same state, you will encounter a blank and then you'll keep on moving. So basically, the first cell that you have to fill in is fixed. And the next insight is be economic. Well, the only difference between these two programs is that in the first program, we transition to the 37th state, but basically it's a new state, a state that we haven't seen before, and it could just as be well renamed to the first state. And basically, if you combine those things with the following insight, is that we also have a question mark there. As long as we don't need to know what the question mark is, so if we make a simulation of the Turing machine, and we never need to answer the question, well, what would you do if I'm in state 0 and I'm reading a non-blank thing? We can just happily simulate it, and we basically what we're doing is we're simulating in parallel a number of Turing machines, and that's what the tree normal form is. If you unfold the thing, so the tree normal form is don't answer questions beforehand, but just answer them just in time. What I started out and what I examination of this. And what you can do is you can examine, and if you follow the term examine, a machine for a number of well, what you can do is you can examine a number of states for a number of times. And if you unfold the definition of examine, this is basically using the tree normal form of a program to explore a machine. So how much time do we have, Rebecca?
You're good. We have the 15-minute break exactly for this reason.
Okay, great. So basically, what I'm doing here is creating a handler for the explore ability. And the explore ability does nothing more than say, I want to explore this machine, and this machine has run already for a number of steps. So as you implement the ability handler, you have to say what you have to do with a piece of continued code that doesn't have the ability anymore, and when it does. And basically what I'm doing is, if you're asked to explore a machine that has already run for a current number of steps, you will simulate it until one of a few things happens. And that is either the machine halts, that's on the first line, or it didn't halt, so you ran out of time, or you asked an instruction for a key, a combination of state and a symbol that the program doesn't know about. And if you if you're in limbo, if you don't know how to proceed, you have to make a decision what kind of instruction you have to do. And the interesting thing is that you can ask basically Unison to tabulate all the instructions and subsequently explore those as well, and then tally up all the results that you have. Okay. So I'm short on time, so I'm skipping over a little of details. If you're interested, I can explore them in the Q&A. And if you then scroll down to the examples, we see that Unison can, or actually the presentation, Unison answers the question correctly for at least the values that are shown in the slides. So the details basically say if you will examine a two-state Turing machine and have a maximum of 15 steps, then the current champion in the number of steps is 6, and you can write at most 4 ones on the tape. And for a 3-state Turing machine, you eventually have to, you will at most take 21 steps, and you write 6 ones, which are the correct values. The only problem is there are heaps of Turing machines that are undecided, that you have to think hard about if they will finish, and that's what basically is done this year. So the value that were 3 years back were still question marks, which were conjectured to be the exact values. This year only, and that's why I really like giving this talk, because when rediscovering the current state of affairs, I learned that that it was resolved. So the values are correct, and they are formally proven to be correct. So why would you want to do this? So if you're like me and you like to philosophize about the nature of things, knowing the busy Beaver number for a number of states of a Turing machine is very valuable, and in a sense, it's a mathematical definition, but you can also maybe say something about consciousness if you're inclined like that. There's a famous problem in mathematics. It's a Goldbach conjecture, and it basically says that every even number is the sum of 2 primes. And it's not known if this is true. People have conjectured it to be true and checked it for a lot of values, but checking a lot of values isn't an actual proof. But I can give you a proof. What I could do is I could create a Turing machine that is searching for a counterexample, basically tallying up all the iterating through all the even numbers and finding primes that will sum to it. And if I can't find an example of that, it can halt the Turing machine. And otherwise, it just will continue on finding an even number that isn't the sum of 2 primes. That Turing machine that I've just created, which is basically writing a program, the Turing machine has a number of states, and if I know the busy Beaver number, so the maximum number of steps a Turing machine can take with that number of states, I can just simulate it, and I will have to wait until that number occurs, until that number of steps occurred. And if it found a counterexample, I know that this conjecture is false. If I haven't found a counterexample, the machine is still running, but the only machine that's running past the busy Beaver number of steps are the ones that never halt. So that will also give me an indication that the conjecture is true. So that's the philosophy of this, and there are some more interesting side facts, but we'll go on to narrow. So this is, to me, it was a fascinating problem, especially also because it was on the cusp of the frontier of science, and you could tangibly do some work on it, because the busy Beaver number, because it is an uncomputable function, it grows very, very fast, and there's no reasonable way to, in my lifetime at least, answer the question what the busy Beaver number for 6 states is. That's why I wanted to talk about this. I noticed a few people in our lovely community that are living in the Netherlands, and that's why I want to mention that we have a Dutch Unison meetup next Wednesday. So if you're in the vicinity of Rotterdam and would like to share your love of Unison in person, please join us. And that's my talk for today.